Hey guys, I'm back, your host Amit Agrawal, with another video, a series of Leet Code. So there's a one more problem here, one more problem statement is here. Binary search tree formation from pre-order traversal. So let's see how we can resolve it and what are the approaches for it. Let's move on to the Leet code, right? So yep, this is the problem statement that we have. So let's understand the problem statement first, and then after we'll go with the approaches, right? As per our earlier first approach is to understand the problem. So return the root node of a binary search tree that matches the given pre-order traversal. So first of all, those who don't know about the binary search tree is a complete tree which basically denotes if any of the element which is like for an example, consider this is a tree, right? But for binary search tree, it would be in a certain situations where you have to check that the root element should be greater than the left subtree, and similarly vice versa we'll go ahead with the left one. So one is the left most minimum value or minimum value of this whole tree. So this says basically it if any of the node like contains any of the left or right child, the left would be lesser one and the right would be the upper one. So this is how the binary search tree gets formed. So this is that is why we call it as a binary search tree, right? So this is a formation of binary search tree. You can Google it if you didn't get understand much better. You can Google it what the binary search tree. I'm sure that in first definition in the definition of these things like this didn't get understand much clearly. So let's move on. I'm assuming that you don't know you don't you know about binary search tree, and assuming that thing, then I'm going ahead. So return the root node of a binary search tree that matches the given pre-order traversal. Now this the pre-order traversal. What is pre-order traversal? So pre-order traversal is an approach by which we can traverse a whole tree. So like we have a different mechanism to traverse a tree. So in that mechanism we have a one pre-order traversal. And pre-order traversal, if you didn't remember quite much or if you don't know about it, so I would suggest you should go for there's two approaches to traverse a tree, where like one of the approaches breadth first search, where BFS, I would say let me just write it somewhere so that you can understand much better. I'm opening a notepad. Yep. So there are two approaches, breadth first search and depth first search, right? In depth first search, like where this pre-order comes in, from where pre-order comes in. So in depth first search, we have a different mechanism, different orders basically, where we can traverse a tree. One is pre-order, right? Second one is in order, and third one is post order. Pre-order, like in a brief introduction about it, it basically says that root element, the root node, right? Root node will come around. This is a pre, right? So pre means the root node is first element, and then left node, and then right node. So what usually happens is like when we are traversing via depth first search approach, we say that root node will be traversed first, and then after its left one, and then after its right one. And in order means like in between, right? So what we will do is left node, root node will be the middle one, and right node. And post order means the right node would be first one, and the root right node, and this one, root node and left node. right? Now you got an idea. So we are seeing here pre-order traversal, root left right, right? So let's see how what we can do. So you gotten some idea about pre-order traversal. So what we will do is we will traverse by first going to the left, and then after going to the first we will go to the root element, and then after left and then right, right? So BST has one more concern that I constraint that I've already told you, that the each node value will be the upper, like the left value will be lesser one in compared to the root node, and the right value would be greater one. So coming to the problem statement, recall that binary search tree is a tree where every node, any descendant node left has a value of less than, right? As I told you, less than. Node dot left has a less value of node dot value, right? This has a less value. So by mean to say is this would be again, and this would be like this. This is a less than sign, and this is a greater than sign. Less, greater, and this would be greater, right? So it means is 1 is less than 5. Who doesn't understand from this figure? So for them, this is an hint, like 1 less than 5. This is how it is represented. So and any descendant of node dot right, and right value is having the greater than of node value, right? So also recall that a pre-order traversal which displays of the node first and traverses the left and right. As I told you, this one, root first, left, and then right, right? So it's guaranteed that the given test case there is a always possible to find a binary search tree with a given requirement. So let's see how it goes. So we have an input of elements where they have given 8, 5, 1, 7, 10, and 12, right? We have to form a binary search tree from out of it. How we can achieve that? So let's say in approach itself, what we can do is, like, first the node 8 is appearing. So what we can do is, like, let me just erase it. So first approach we can do is, like, we can create an 8 element, right? Got it? First we got the 8, now we got the 5. So what we will do is, like, we will go by the condition that hey, okay, I'm 5 8 is, I'll check 5 if 5 is less than 8 or not. If it is less than, then it will be on the left side, right? Got it? Now coming to the 1. Now 1 again, since this is a current root node, this is a root node, so now I need to traverse the whole tree to find that node where I can insert this one, because first and second element are easy to insert, but after the third element we have to iterate over the tree so that we can find the best location to insert that element, right? So to insert this one, we need to find the minimum location, like a minimum location, or the path where we can insert the minimum value, right? So now on the root side we will iterate towards the 5. We see that 5 is the lesser one, and now if I compare with 1 and 5, right, 1 value is less than the 5, so it will be again inserted to the first. Now 7, we got the 7. Now we need to compare with the 5. Again iterating will start from here, and it will go to the 5, and because 7 is less than the 8, so it will go left, right? It will go to the left, but 7 is greater than this, so 7 though sorry 7 is greater than the 5, right? So this is how the, right? So what we will do is we will create a 7 node, right? Similarly, it will go for the right case. It will see for 10 and 12, right? So for each every element, we have to find out a position where we can insert that element, and this is how we are going to process. So now let's see what we can do to in order to resolve this problem. So we have a two approaches here, like to resolve this thing. Like one way is to iterate towards each and every element, or second way is recursive. So like there are two approaches. From there we can approaches that we can follow. One way is iteratively. Second way is recursively. We are going to see both of them. Like I have provided a solution for both of the problem statement. So I'm not gonna write to the code here because it will again lengthen this video call or video length. So that is why I'm gonna show you the code how it is going to be work, right? So first we will go with the iterative one, and then we will go with the recursive one. Or like if you want to, like, because most of the solution are provided with the recursive one. So like if you go to the Google, and you'll find out there are so many solutions out there which are provided by the recursively. So as we follow along with the approach that we have to iterate each and every time, and we are finding out. So for in the first example, first step, if the root node is null, then we will provide that thing. So let me just go and open the code so that you can get an idea what I'm talking about. So as I told you, like the let's see the recursive approach, right? So I'm just opening the recursive approach here. So I'm just opening with the whiteboard so that the things can get more clear, right? So if you see this problem statement here, what I am doing is forget about this piece of code. I will come to this point. Just see, this is the starting point of this function, because this is a function basically, right? So if I do something function, and if I remove that thing, this is the same way of writing this code. So forget about this code. I'm just hiding it for now. I'll so first what I'll do is I need to find out the root element. Since the A is the basically array, I would say a array, right? Let me just array for your understanding. Right, so step first is basically to find out the root element. So if let's say, because we are going to construct a binary search array, right? And the helper functions that we are given is basically the tree node, where value left and right, this value left and right. So consider a case where one node is present, and this is given a empty value, and left and right are the two pointers to it, right? So we are structuring in that way. So each and every node will be having those three attributes inside that node, right? Got it? So moving on to the resolution. So first approach is to find out the root element. Since we are going to construct a tree, so first we are calculating the root element, and root element will be the first element of that array, right? Got it? The first element of that array. And if you can do one more thing, I have didn't write it here, but this is a mandatory step, validate input always, right? And then after go to the below step. So this is a step one, find create root element, root node basically, right? Step two, iterate over each element in array, in given array, right? So the like first we have calculated the root element, which is this one, from this array. If the root doesn't if this array does not contain anything, so we will return the null. So in this case, if not equals to array, return null, right? This is how we can validate. Or you can write in separate function where you can basically calculate your uh, all those corner cases. So this is always recommended that you should write your own test cases or own corner cases in order to validate this scenario with other inputs and output. So right, so we'll go ahead with the second step, and second step is like iterating over each element of this array, right? From this, because from this we have got the root element. Now this will be the again second one. So here we are iterating from the 5 itself, and if I come to the problem statement, so I'm iterating from the first element of the array, and I'm searching this the root element. So I'm finding out that position, right? As I told you, I'm finding out that position where the root element or the node element can be inserted. This element, basically the 5 element, can be inserted. So now let's see to the search algorithm. Search is basically searching the position where we can insert that element. This is a recursive approach. Recursive, why recursive? Recursive approach. Sorry guys, this video gets lengthy because I'm giving you a line by line understanding. So it takes time to understand the things. So that is why this video gets lengthy little bit. But I'm sure you'll by the end of this video you'll understand some of the concepts of the binary search tree as well as the traversals. So this is the most common and most widely used problem statements inside the tree traversals. So let's see the search function. So I have created an inner function called search, where I'm passing two parameters to it. Arguments, basically root argument and the value argument. Root is basically the root that I've created, so that this element, from this element I can search on, and the value which I'm going to insert, right? So now, since this is a binary search tree, right? As as I told you that this has some constraint that all those lesser value will be on the left side. So I'm already checking that thing, that third, if the value is greater than the root value, then greater value, or if the value is less than, sorry, less than the root value, then uh, then search in the left subtree, right? So we will go to the left subtree. So it means we are going here, right? If we compare with the 5 to 8, so 8 is here, 5 is here. So if I compare, 5 is here, 5 less than equals to 8. So 5 is less than, so it will come here. Because 5 does not have any element, so it is a null element, right? It is not created yet. We are going to create it. So if this is a left element which is a which is a null, so we will directly attach that node to the left tree, right? Or we can do one more thing, like we can create a simple let node equals to new tree node, where value, and each time we found any position, we can attach that node, right? Got it? So we have created a node out of this value, and attaching that node if we find any of the null value to it. So let's say in this case 5 is because 5 was not created. Let's say 8 is this case, and this has nothing to it, nothing left to it. So that is why we have attached that node element to the left. Now if let's begin with another one value, and one, now we need to traverse to the 1. So we got this 8 and 5, like we have got this 8 and 5. Now we need to insert the 1. So 1 is again left, and now the root left is already having the 5 elements. So it will go and say that okay, search for root and left. So now I'm making the another recursive call to find the left subtree, left of it, right? Left of this 5 element. So that is why I've called it root dot left, and the value that is going to be inserted, right? Got it? This is the thing that we have done here. So we are providing the value, and it will calculate the node, and it will attach that, right? And secondly, yes, now I'm coming to the right portion to it. Right portion is the 10th is greater than this. So greater, we do not have value any, so we will attach that code. And again, if this is having that 10th node again for 12th, let's say we are traversing 12th, then 8 is less than the 12th, so it will go right. And then 10 is again less than of 12, so 12 will be the right of 10. So that this is why the right of value is going to be returned here. Now the search function will be completed and it will return me the root. Because we are working on the pointer, so we are providing the root pointer, and this is the memory references where we are working on. So that is why we are not returning anything to it, right? So you don't need to worry about like why we are passing the root function, root element, and but we are not returning anything. But because we are passing the reference here, reference of the root element, and all these are nodes that are getting attached to that reference in the memory location itself. So that is why the root is going to be returned with all those elements that are attached to it. Now we are going to see quickly iterative approach to it. So let me just run this function so that you can get an idea how it is working. Right, let me just see. I've made some changes to it. If it does not, okay, that's perfectly fine, I guess. Let's see how it goes. Accept it, right? So let's see with another iterative approach quickly. So the iterative approach is this one. Iterative approach. Earlier we were seeing the recursive one where the call stack was preventing all those calls, and we were returning the functions, search functions again and again to iterate over left and root child. But here we are little different. We need to provide a manual stack which can keep track of, which can hold the history of all those nodes that are processed or that are traversed basically. So we are going to create a stack here, like we are going to create a stack, and in that stack we are going to insert each and every element so that we can iterate towards them. So what we are doing is, again, we are first approach is to create the root element, right? We have root element is created. Now this is the stack. As means stack here, right? As is the basically short form to it. So stack, in the stack itself, I am storing the root element, right? So I've provided the root, right? Root element, and I'm iterating towards each and every value that I've already told you, that pre-order each and every element I have to traverse from first of the value, because I have one value I've already inserted inside the stack. So I'm iterating towards it, and I'm getting the first value or of this index, and I'm creating a one current function which will calculate the current position to it. And now I need to iterate towards that stack. Like if that stack is not empty, first I am checking is that not empty, and till the time it is not empty, and as well as if the value is greater than the value is greater than the stack last value, or the basically the top value of the stack. So let's say the stack is full at here, so I'm checking this condition, peak value, basically I would say peak value. So I'm checking here the peak value to it, and I'm popping out each and every peak value out of it so that I can get the last element which got traversed. For example, just to understand much better, let's say in this example 8, 5 and 1, we have traversed to this element. Now we need to process the first element, and then 5 and then 8. So we will pop out this last element, then this, and then this. Got it? This is how it is getting worked, right? So let me just clear so that you can get much more clarity to it. This is how we are processing that thing, the peak element. I'm saying that peak element, and as well as I'm comparing this should not be empty one. So what it can do is it can pop out all those values till the time it is not greater than, right? So I'm checking all those left values. So if this is not null value, the current element is not null. If it is a null one, what we are going to do is, like, we are going to attach that node that we are having, right? So what we are going to do is, like, we are going to attach this node, and attach means, like, I'm going to push that element inside and I'm going to push that left portion of it, like whatever I've attached it, I'm going to attach this thing inside the stack. Earlier we were using the in recursive methods, the all those stacks were already being created by the compiler itself, but right now we are keeping track of each and every records inside our own custom stack, right? So the same pattern is goes here. If we didn't find any value, like if it finds a current pointer, then it is going to attach to the right element, because we are iterating towards any of the value that is greater than. So greater means is, like, I have traversed all those left subtree, and now I am going to process the right one. So that is why I've processed all those left values. Now I'm going to process the right one. This is how it is going to be done, right? So that's it, guys. This is how the iterative approach comes in. So iterative approach, we have to create a stack to keep track of each and every element, but in recursive you don't have to create. It is by default created by the compiler itself for you. So that's it, guys. If you did get any of the things from my video, or if you find any of the things useful inside it, please do like and subscribe. I'm waiting for your comment also. Thank you, guys. Bye bye. See you next time.